In Chapter 3, we're going to be looking at counting problems and different ways that we can count the number of outcomes or the number of possible scenarios in a given problem. We're going to be looking at permutations and combinations. And in general, let's skip down to the generalized formula. If we have a task that's going to be carried out in our stages, there are n1 ways for the first stage, n2 for the second, and so on, then the total number of ways that we can accomplish the task is going to be the product of each of the number of ways that we can accomplish the different stages in the task. And then we can go through and add all of those together. We can form a tree diagram for these various scenarios. So for instance here, if we have a choice of soup or juice, and then to start off the meal, and then for our main course, meat, fish, or vegetable, we have that choice for both soup or juice, and then for each of those main dish options, we can choose for our dessert either ice cream or cake. And so we're going to count the total number of leaves on this tree diagram, so those final branches that we end up at. Now we can use this in combination with other techniques, so we can assign probabilities to events, or we can use it to count things where we have different choices depending on what initial choice we make. So for instance, let's say we have a choice of coffee, tea, or hot chocolate. Then if we get coffee or tea, we can choose to either have cream, milk, or to have nothing in it. And we can also choose to have sugar or nothing for each of those choices of cream, milk, or nothing. And if we got hot chocolate, we can choose to either put whipped cream on it or not, and we can also choose to put cinnamon on it or not. So our tree diagram would start, and if we wanted to draw that out, we could say, we could go to coffee, tea, or hot chocolate. And then for the coffee choice, I can either choose cream, milk, or nothing. Similarly for tea, cream, milk, or nothing. And then for the hot chocolate, I can choose whipped cream or nothing. And then for each of these choices, so if I choose coffee with cream, I can either have sugar on it or not. Same thing for these others. And when you're drawing tree diagrams, be sure you leave yourself enough room for all of your options. And then on the hot chocolate choices, I can either have cinnamon or nothing. And then we're going to go through and just add up the number of ending results here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different ways that we can do this. So 16 different choices. Now the other way that we could have gotten to that 16 would be to take our coffee and tea, so I have two choices there, times, so we're going to look at the number of ways that we can choose coffee or tea, and then we're going to multiply that by 3, the number of cream, milk, or nothing choices there, multiply that then by 2, and we end up with 12 from that. And then for the hot chocolate, we can choose, so there's just one choice on that branch, and then we can choose whipped cream or not, we can choose cinnamon or not, so we get 4 options there, and then add both of these together to get our answer of 16 again. If I wanted to assign probabilities to these various events, so let's say given a random person from a population, maybe they have a 50% chance of choosing coffee, a 30% chance of choosing tea, and a 20% chance of choosing hot chocolate. And then of the coffee drinkers, maybe 0.4, so 40% choose cream, 40% choose milk, and 20% choose nothing. And then of those who choose cream, 80% choose sugar, and 20% choose nothing else. we get the probability that we have a coffee with cream and sugar drinker from our population by multiplying the three probabilities that correspond to this leaf in the tree together. So this event is going to have a probability, so that I have coffee, cream, and sugar is going to be equal to 0.5 times 0.4 times 0.8, or 16%. And then if we were to go through and assign probabilities to the rest of these branches, I won't do that for all 16 choices, but if you do that and compute the probabilities for each of these end results and add them all together, then we should end up with a total probability of 1 for all of them. If we wanted to find the probability that a person chooses sugar, say, then we would look at all the sugar outcomes in the final result here. So I'd have this 0.16 plus the probability that we choose coffee, milk, and sugar, coffee, nothing, and sugar, and then tea, cream, and sugar, tea, milk, and sugar, and tea, nothing, and sugar. So you'd look at those 6 different outcomes and add up the probabilities for all of them to get the probability that a person chose sugar in their drink. And another fun probability and counting type problem is the birthday problem. You may have heard of this before. The probability that 2 people in a room have the same birthday, so day and month, not year. You could also do it with year, but then you need more people to get the result. So there are 365 different possible birthdays. So if I have 366, I guess there are 366, they're not counting leap year here in the book, but if we do count that, if I have 367 different people in a room, then I'm guaranteed that 2 of them, at least, are going to share the same birthday. But if we look at the probability that 2 of them have the same birthday, we actually only need, as it says here, 23 people in a room to get a greater than 50% chance that they will have the same birthday. And we'll try this in class, maybe on Monday, see how it works out in our sample space. But there, we're looking at all of the different choices for birthdays, and going through, taking the product of all of those. And we're doing this by looking at the probability that we don't get any duplicates at all, so that you look at the probability that nobody shares a birthday and then take 1 minus that, and that'll give you the probability that at least 2 people have the same birthday. And if you run through and compute that, turns out you need, again, only 23 or more to have a greater than 50% chance that 2 or more people have the same birthday. So I'll come back and look at that on Monday a little bit more. The other main topic that I want to talk about in this section are permutations. And these are just different ways of ordering objects. So for instance, if I have, let's just write these out. Let's say I have the numbers, just use numbers because that'll be a little bit easier to draw out. Colors would be prettier, but it's going to take too long. So let's say I have the numbers 1, 2, 3, and 4. There are different ways that I can permute these. So I could have 1, 2, 4, 3, so just rearrange those numbers. I could have 2, 4, 3, 1, 4, 3, 2, 1, and so on. So all these different arrangements. And when I look at the number of ways that I can arrange these 4 numbers in a given order, I have, for the first slot that I go to fill, I'm going to have 4 choices. And then for the next one, I've already used up one of my numbers, so I have 3 choices there, and then 2 choices for the next, and then finally at the end there's only 1 choice for what goes there. And so the total number of permutations is going to be equal to 4 times 3 times 2 times 1, which is equal to 24. And the other way that we'll write this is factorial. So this is 4 factorial, and in general, n factorial is going to be n times n minus 1 times n minus 2, and so on. You carry that pattern down until you get to 1, so 2 times 1 at the end. The special definition, I don't know that we'll run into this too often. 0 factorial is equal to 1 by definition. If I think of that in terms of permutations, if I have 0 objects, then there's exactly one way to arrange them in a particular order. Sort of vacuously true argument there, but that's another way that you can think of the 0 factorial being equal to 1, or we just define it that way. There's another way to define factorials in terms of what's called the gamma function. We're not going to get into that, at least not at this point in the course. And using the gamma function, you can actually define factorials for fractions and not just integer values. And the gamma function, if you evaluate that at 0, you end up getting 1 back out of it. Alright, but going back to our counting scenario, so if I have just a finite number of objects, I want to arrange them or I want to permute them, shuffle them up, rearrange them, then we're going to get n factorial ways that we can do that. If I only want to choose a certain sized subset, so for instance here, if I want to just pick 2 of the 4 objects, then I'm going to have 4 times 3 ways that I can choose 2 of the objects from that group of 4. Now the book goes into a form of the notation for permutations that's a little more abstract. So one way that I can write a permutation, and we'll use lowercase sigmas oftentimes, let's say I want to take this permutation right here. This is going to be equal to, and we're going to write this little n by 2 matrix. I'm going to have in the top row, I'm just going to write out the elements that I'm starting with, and then I'm going to write beneath that where they get sent to. So 1 is going to then become 2, 2 becomes 4, 3 becomes, or stays 3, and then 4 becomes a 1 in that permutation. Now typically we're going to list the top row, just 1, 2, 3, 4, just have the normal ordering there, and so we can look at just that bottom row instead. And we can also have what are called fixed points in a permutation. So an element that ends up staying in the same position, it stays just by itself there. So for instance, right here, 3 stays in the same position that it was before, and so that's going to be what's called a fixed point in this permutation. So it didn't get sent to any other element. They also talk about records in the book. So a record is going to be the highest value that we've come to so far. So for instance, in 2, 4, 3, 1, 2 is a record because it's in the first position. And 4, if I were looking at that, that would also be a record because it's bigger than all of the elements that I've listed out before. 3 and 1 would not be records, so 3 isn't bigger than 4 and 1 isn't bigger than any of the things that came before it. On Monday we'll go through a few more examples with permutations and probabilities and illustrate some of the ways that we can use the ideas from this section. But we're just starting with these very basic counting ideas. If you've had discrete already, then we've covered pretty much all the counting stuff that you would see in this section in that course with our basic counting that we went over there. But we'll do a few more examples and tie the probability back in on Monday.